As we saw yesterday, the correlation coefficient is a very nice way to describe the strength of a linear relationship. We know that the correlation coefficient ranges between -1 and +1. If we have a value of -1, that means that our data set would contain a negative slope, and all of the data points would live exactly on the line of best fit, meaning that there's basically there is literally no scatter away from the line of fit. If our correlation coefficient's +1, our data would have a positive slope, and it doesn't matter how steep it is, it would just have to be a positive slope, and all the data points would literally be on the line. As the data points scatter away from our line of fit and the scatter becomes larger and larger, the correlation coefficient moves towards the number 0. And although the correlation coefficient is widely used to describe the amount of scatter in a linear association, it is unfortunately an arbitrary computation. Correlation coefficient does not have a real-world meaning. And what we want to do today is develop a meaning so that we can describe correlation coefficient in context and talk about what exactly it's telling us about the physical situation we're looking at. Let's jump down and take a look at the math notes in this section. Correlation coefficient R is a measure of how much or how little data is scattered around the LSRL. It is a measure of the strength of a linear association. The correlation coefficient can take on values between -1 and +1. If R is 1 or -1, the association is perfectly linear. There is no scatter about the LSRL at all. A positive correlation coefficient means the trend is increasing, slope is positive, while a negative correlation means the opposite. A correlation coefficient of 0 means the slope of the LSRL is horizontal and there is no linear association whatsoever between the variables. The correlation coefficient does not have units, so it is a useful way to compare scatter from situation to situation, no matter what the units of the variable are. The correlation coefficient does not have a real-world meaning other than an arbitrary measure of strength. Interestingly, if you take the value of the correlation coefficient and you square it, we get something that does have a real-world meaning. The value of the correlation coefficient squared, however, does have a real-world meaning. R squared, the correlation coefficient squared, is written as capital R squared and expressed as a percent. The meaning is that R squared percentage of the variability in the dependent variable can be explained by a linear relationship with the independent variable. Now that is difficult to comprehend, that's difficult to interpret, so there's an example below that, but I do want you to think about and probably even write down this very sentence, right? Its meaning is that a certain percentage of the variability in the dependent variable, that would be the y variable typically, the variation away from the line of best fit, a certain percentage of it can be explained by a linear relationship with the independent variable. Okay, so for example, if the association between the amount of fertilizer and plant height has a correlation coefficient of 0.6, then R squared, or R squared, is 0.36, so that's literally zero point 0.6 squared. And we can say that 36% of the variability in plant height can be explained by a linear relationship with the amount of fertilizer used. So 36% of the variation in that. So more fertilizer, the plant will grow better, less fertilizer, right? But the thing is that there are other things that contribute to the plant height. It's not just the fertilizer. The rest of the variation in plant height is explained by other variables, like the amount of water, the amount of sunlight, the soil type, and so forth. The correlation coefficient, along with the interpretation of R squared, is used to describe the strength of a linear association, the strength. So at this point, there's three things that we should be able to talk about in fairly strong mathematical terms about the association between two variables. We should be able to talk about the shape of it, and not just looking at the shape in terms of the scatter plot, but also ways to test whether or not a particular shape is appropriate, particularly a linear association. Should a relationship be modeled by a line, yes or no? The direction's fairly straightforward. How do we know the direction, the movement of the data? And then also the strength of the association. What tools do we have to talk about the strength of the association? And what does it mean in terms of context of a particular problem? The metrics that we use for measuring strength, what do they mean in a particular problem? Always be looking at the x-axis and the y-axis in terms of like what they tell us about a situation when we're describing it. In a minute, I'm going to have you write a response to a prompt, and that'll compose the bulk of today's assignment, a written response to this prompt. But let's look at two problems from today's section first. You're going to be completing problems 95 and 96. 95 does have everything set up in Desmos already, so you're not going to have to type these values. But when Julia went around town in problem way back in 49, several sections ago, comparing the price of pizza, she gathered this data. Okay, nice data. And it's already set up in Desmos, so we can just click here and open up the Desmos eTool and look at it there. The question is, what is the least square regression line? And we are supposed to interpret the y-intercept in context. So what does the y-intercept mean in this context? What is the correlation coefficient, and what is r squared? So both of those are calculated quite nicely for us in Desmos. Even if it didn't give us r squared, we would literally just have to take the correlation coefficient and square it to get it. But remember, r squared tells me it's expressed as a percentage, and it's the percentage of variation that is attributed to a linear relationship between the dependent and independent variable. And then part C says, in problem 49, you wrote a report describing this association. Now improve upon that report by making it more mathematically precise and quantitative. Use slope when describing the direction, and use a sentence about r squared when describing the strength. So again, I would suggest referring to the math notes in this section when thinking about r squared. But that's the first of two problems I want you to do. The second problem is what Julia's father finally decided to do now that he's opened and he's selling pizzas. So Julia's father finally opened his pizza parlor. He charges $7 for a cheese pizza plus $1.50 for each additional topping. Choose 4 or 5 points and make a scatter plot of the price of pizza versus the number of toppings at Julia's father's pizza parlor. What is the least square regression line? Interpret the slope and y-intercept in context. What is r? What's r squared? Write a sentence about the variation in the price of pizza at this parlor. Explain in context the difference between this r squared and the one that you calculated in the previous problem just above in 95. And actually, I think that's going to be it for today. So this is a great opportunity to kind of consolidate your understanding about associations between the independent and the dependent variable, and think about and talk about shape, direction, and strength. So we will leave it there today, and we are now wrapping up chapter 4, and I will see you in class and online again soon.